Uh, Hello everyone, welcome to the sixth lecture, I think, of number theory. Today we will start getting a bit deep into number theory. Till now, can anyone tell me what all you have learned?
Factorial base system.
Base system.
The
What else?
yes, base system, divisibility, and the properties, and HCF and LCM.
Okay. Have you solved problems from this?
Yes.
Okay. Anyways, my handout has these topics and problems also. Not base system. Base system, the PowerPoint is enough. Also, you can read Holland. Okay, so let us get started. So, like as you all know, number theory is the study of this set of integers. Okay, and their properties, various properties. So, let us study this theorem called the fundamental theorem of arithmetic. By the way, am I audible clearly?
Yes.
Yes, sir.
Okay. This theorem, I think many of you have already learned in class 10 in your school syllabus only. This is a very important theorem. What does the theorem say? The theorem says that any natural number can be factorized uniquely as a product of powers of prime numbers. So basically, if you have any natural number, okay, so you can factorize it like this: p1 to the power e1, p2 to the power e2, so on, pk to the power pk. Where p1, p2, all these are primes. These are prime numbers. All of you know what are prime numbers, right? This is the sixth lecture, so I think all of you should know what are primes. And the e1, e2 are the highest powers dividing n. For example, uh, someone, okay, let us take 72. Someone factorize 72. What is the highest power of 2 which divides 72? 72 is divisible by 2.
Take 3.
Sir, I guess
Sir,
3.
2 cube.
Sir, I guess 3.
Sir, 2 cube.
Okay, 2 cube
2 to the
into
power
what?
3
Answer
Into
3
into 3 to the
square.
power 2.
3 square. Okay. So this is the unique factorization of 72. Now the fundamental theorem of arithmetic says that any natural number can be factorized like this, and that factorization will be unique. Like you cannot get some p1 to the power e1 into p2 to the power e2, where p1 and p2 are not these, and e1 and e2 are not this. There is only one possible representation, which is 2 cube into 3 square plus. Now the proof of this theorem needs induction, and Sabyasachi sent the link in the group. It is in my handout also. You can watch it later. Let us move forward. Uh, so one important thing is observe that I can write this as 2 cube into 3 square into 5 to the power 0 into 7 to the power 0 and so on. Okay. Like if there is not a prime, then I can just put that to the power 0 in the factorization. Makes no difference. Right? Oh wow, 12 people joined. Hello, 12 people. Okay, so now that you know the fundamental theorem of arithmetic, let us quickly recap divisibility. Okay, before that, just a question. Uh, which okay, wait. Find an integer divisible by all prime numbers. Can someone tell me the answer?
The product of all prime numbers.
Yeah, so like let us
There
do
are
it.
infinite prime numbers, I think.
Yeah, so if you multiply infinite prime numbers, then the product will also be infinite now. Because the numbers themselves are like they are not fractions. If you
So
multiply
I think
half
there is
infinite
not a
times, then
particular
it will
integer,
go to zero.
the answer.
Yeah, like yeah, basically, see, infinity is a not a number. You can only go towards infinity. You can never reach infinity, right? So I can't say
Yeah.
that infinity is divisible by all prime numbers. Infinity is not even a number. You can go towards infinity, but infinity is itself not a number.
Sir, can I ask a
Infinite,
question?
yeah, ask.
Sir, what is infinity minus 1?
Yeah, so if infinity is not a number, so how can you subtract from infinity? Like the color of my uh, house is yellow. Now, if I ask you what is the color of my house minus one, yellow minus one, what is the meaning of that? There is no meaning, right? What is the meaning of yellow
Yes, sir.
minus
No.
one?
Yes, sir.
So infinity is also not a number. We make this mistake often. Okay. So the answer to this question, anyone else would like to try? Not anyone else. Like even if you want to try once again, you are free to try it. And an integer which is divisible by all prime numbers. Okay, notice the word integer, not natural number. Huh?
Yes.
Yeah, now think. It
Sir,
is a
can I tell?
very yeah, sir.
The zero?
Yeah, very good. Zero is divisible by all prime numbers. Can you explain why?
Yes, sir. Sir, we know
Huh.
that zero by any number gives a zero only. So, sir,
Zero
as we are
by
given,
p equal to zero. Yeah.
so sir, it should result as it is divisible. Therefore, zero by that number will result an integer only. So, as zero
Yes.
by any prime number, if we divide it, we are getting an integer which is zero itself. So, sir, it will
Hmm.
the answer will be zero.
Yeah. So if m by n belongs to integer, then n divides m, right? Like
Yes,
6
sir.
by 3 is
Yes.
equal to 2, which is an integer.
Yes.
So 3 divides 6. So similarly, now if I replace m by 0, 0 by any prime number equal to 0, which
0.
is an integer. So 0 is divisible by not only any prime number, it is divisible by anything you want. Okay. Like even if you want to divide it by product of two primes, what not. Like basically in this expansion, p1 to the power e1, p2 to the power e2, whatever you take, it is divisible by everything. Not only all primes, like even 6 divides 0, even 15 divides 0, 72 divides 0, everything divides 0. 0 is divisible by everyone, all the integers. Okay. So like often this technique is called infinite descent. Uh, Wait, I forgot the spelling. Whatever it is, it was made by the mathematician Fermat again, about whom we were speaking last time. You remember Fermat's last theorem?
Yes, sir. For
X
Mark
n
sir.
plus y to the power n equal to z to the power n. No
Has no
solution for n.
solution if n
Ah,
is greater than
yeah, yeah, right. So this format guy, he only made this technique infinite descent. So what does this technique say? If you see, this is my version basically. In
2.
and uh, your voice was breaking. You were speaking. Okay. Acha, if you let me continue. If you see in a number theory problem, let, in a number theory problem, that some number, okay, is divisible by anything, all primes or something like that, then that number is zero, pakka. Remember this trick, very important trick. Acha, if you want to copy, let it. अच्छा, तुम लोग चैट में क्या स्पैम कर रहे हो? Whatever.
Yeah.
हाँ, sir.
Can you once repeat what was the infinite descent?
So like you understood this now, that zero is divisible by all prime numbers,
Yeah.
and there is no finite number other than zero which can be divisible by all prime numbers, because
Yes.
there are infinite prime numbers, and like my number will always be less than some prime, and infinity is not a integer, so only option is zero. So basically infinite descent is saying that if you find a number in some question where it is satisfying the property that it is divisible by all primes or all integers or something like this, then that number is zero. Okay.
Yeah, got it.
Okay. Okay, so now divisibility. What is divisibility? You all know this. So A divides B means that B equal to AX for some integer x, and A is not zero. Okay, because you cannot divide by zero, that you all know. So there are some properties of divisibility. These properties have been covered in class, I know. A divides B and B divides C implies A divides C. This one you know, right?
Yes, sir.
Yes, sir.
Okay. So now my question is, someone prove this. Knowing
Sir,
and all
can I
is
tell
fine,
the
but
proof?
proof. Yeah, sir.
Sir, as B is divisible by A, so sir, let's consider B by A to be K1, which is an integer.
Okay.
So sir, B is equal to AK1. Sir, this is first equation. Now,
Yeah.
sir, we are given that C is divisible by B. So let us consider that C is equal to BK2,
Hmm.
which is where K2 is an integer. So sir, it will become C is equal to AK1 K2.
A K1 K2. Huh.
So sir,
Equal
C
to
by
A into integer. Yes. Done.
yes, sir. So sir, C by A is an integer. So C is divisible by A.
Good. Very good. Okay. So there are many more properties which you have learned in class, like this one. A divides B and A divides C. Uh, this implies A divides any linear combination of this. Okay. Now someone else where PQR again integers. Okay, now someone else attempt this proof. Someone else, please. Prove
Sir,
this.
can I tell?
Are, are you the one who told last time?
No, sir.
Oh, okay.
Sir, here we are given that B is divisible by A and C is divisible by A. So, sir,
Huh,
let B by A is equal to K1.
huh.
So, sir, B by A is equal to, so, sir, B is equal to A K1.
Okay.
Now, sir, if we multiply P to both the sides, so, sir, PB is equal to PA K1.
Yeah.
So, sir, as P is an integer, therefore, sir, so, sir, like if we take A down, so, sir, PB by A is equal to PK1.
Okay.
So, sir, as we know that K1 is also an integer and P is also an integer, therefore PK1 will also become an integer.
Huh.
So, sir, that means PB by A means PB is divisible by A.
Okay. Good.
So, sir, now similarly, if we take C by A as K2,
Huh. So from there it will get A
sir, GC
divides
will be divisible by A.
QC. Huh. So
So, sir, now if
and
we add them, so, sir, we will get
yeah.
that will be proved.
Okay. Acha, so now someone else tell me that why if you add it will still be divisible. Like A divides K1, A divides K, not K1, K2, but huh. A divides M, A divides N, A divides M plus N. Prove this. Someone else.
Sir, can I tell?
You are only saying from them.
Okay, sir.
Someone else, please.
Just a minute.
Okay.
Because both of
Okay.
them are the multiples of A, because we know that A divides them. So if we add them, we get another multiple of A.
Yeah, that is my question. Why? The thing which you said, why does that happen? That is exactly my question.
Is it
We get
because
the HCF as A.
No, it may not be HCF.
I guess the denominators are same in both the cases. Is that why?
No.
So one
Okay,
of the factors will
let
be
me. Yeah,
I
one
am
of the
trying. Yes.
factors will
Sir, can
be
you
A.
wait a minute? I am trying.
Okay. Okay, just a hint I am giving. Uh, Here is the definition for divisibility. I'm just highlighting it. You people said you have studied divisibility, still you can't prove these simple things. Shame, shame.
Sir, can I tell?
I know, no.
Okay, sir.
Acha, fast, please. Kavish.
If we take A by M as K1
Ha,
and A by N as K2, then A by M becomes, sorry, A becomes K1 into M, and A becomes A1 into K1, K2 into N. And when we add them,
wait. A becomes
K1
K1M
into M.
and K2N.
Yes,
Okay.
so we can take A M K1 and wait 1 second. Sorry, I got confused.
I think you made a mistake here only. It will be m by a
Yeah,
equal to
yeah,
k1.
yeah.
Hmm.
Then it's we can take a common and then it's done.
Okay, wait. Complete your proof first. Let me write it down for everyone. Hmm. So m by a equal to k1,
And n by
n
a
by
is equal to
equal
k2.
to k2. So m
Therefore, m
equal
is
to
equal to
a k1,
k1.
n equal to a k2. Now what?
If we add them, then we can take a common, and a into k plus k1 plus k2 is means a divides k1 plus k2 because both of them are integers. Hence proved.
Hence proof. Very good. Okay. So similarly, there is another property. Acha, rest of the properties proof is homework. I will not prove everything. A divides B and B divides A. Okay. So A equal to plus minus B. This means either A equal to B or A equal to minus B. This plus minus sign, if someone does not know, that's this plus minus sign basically means it is either plus or minus. It can be any of the two. Proof. This proof is homework.
Sir, now or now? Homework.
Home. Not now.
Sir, I can
Now,
prove.
okay. Home. A
Okay, sir.
divides B implies B equal to 0 or equal to mod. Okay. In when both are natural numbers, so they are greater than 0, then A less than B. So this is a very obvious thing. Like if 5 divides 60, then 5 is less than 60. है ना?
Yes.
Okay, this will be less than equal to it. I have many typos. Wait, let me. I am. Wait, let me note down all the typos. I am noting from my. Uh, अरे क्या कहते हैं उसको हैंड आउट only. Anyone has any problem in this statement? Till then, please tell me. Hmm. Okay, let us move forward. Now, uh, so if P divides AB, here P is a prime, then P divides A or P divides B. Okay, this is not true if P is not a prime. Okay,
Okay.
for example, 6 divides 36, right? 6 divides 36. Now I can write 36 equal to 9 into 4. 6 neither divides 9 nor it divides 4, but it divides the product 9 into 4. So this statement is only valid for prime numbers. Keep that in mind. And the proof is homework. Why is it only for prime numbers? And similarly, P divides a to the power n implies P divides a. This one is similar to the previous property. And from here we can say P to the power n is divides a to the power n. This entire thing proof is also homework. Acha. By the way, in this property, this one, Let me take a few more examples because you are studying it for the first time. So it is good to build intuition. Ah, so what did I say? Mod A is less than mod B. But when AB is natural, then only A is less than equal to B. Otherwise, if A divides B, implies A is less than equal to B. This statement usually is not true. Only for naturals it is true. Let me show you an example. Uh, Wait, I have to. 5 divides minus 20, right? But 5 is less than minus 20. Is this true? No, this is not true. Understood?
Yes, sir.
Okay. So these were the properties of prime numbers. Now let us solve a question. This question came in ISI exam. ISI is for Indian Statistical Institute. It is the best college for statistics and maths in the country. And in their admission test after class 12, this question was asked. Okay, so the question is, let D1, D2, dk be all the factors of a natural number n. Okay, small n. These factors include 1 and n also. It is given to us that d1 plus d2 plus so on till dk equal to 72. Now you have to what is the, it was an MCQ question, so what is the value of 1 by d1 plus 1 by d2 and so on plus 1 by dk. Okay, so let me tell you the answer also. You just have to prove that this is the answer. So try to solve this. If you can, raise your hand. Don't start saying the solution. I give you 3 minutes. Everyone understood the question? No? Question is clear. Anyone who did not understand the question? Acha, Sabyasachi you have solved. Hello, Sabyasachi. Acha, acha. Okay. Everyone understood the question? Anyone who did not understand, please tell me. Acha, 1 minute gone, 2 minutes left. Anyone else, if you solve this, please inform me. Just raise your hand if you have solved the question. Oh, Sabyasachi, you have given the solution. This is not done. Don't see the solution, people. Solve it yourselves.
Actually, they're attaching all the links of the solution in each and every problem.
Are
He isn't solving them actually.
Okay, 1 minute left. Anyone else, if you have solved this, please tell me.
Sir, just a minute.
Okay, okay. 1 minute is there. Acha, by the way, my screen share went off, na?
Yes, yes, it went off.
Okay. Let me share that. Sorry. Okay, so did anyone solve? Acha, even if you did not solve, just tell me what ideas you have, na? Let me listen to your ideas.
Sir,
Sir.
well, it is given that like we have to prove it basically. So sir, d1 plus d2 plus dot dk is equal to 72. And sir, 1 by d1 plus d2 dot dk, 1 by dk is equal to 72 by 9. So sir, if I consider
72 by
these
n.
two, yes sir,
72 by n, not 9.
yes sir, you gave it
Ha
sir.
ha. Continue, continue.
So sir, if I consider these two as two equations, 1 and 2, so sir, by dividing 1 and 2, I am trying to prove that we will get n as the answer.
Acha. That you can do, but for that you have to know the answer. Like in the original exam, it was an NCQ, so I just made it easier for you. But the actual question, you did not know the answer beforehand.
Okay
Okay,
sir.
let me solve it.
The we can pair the things like first and last.
You can say tell
So
your
d1
approach.
into dk will be n. d2 into dk minus 1 will be n.
Why
Like
why D1 DK and why?
I mean, for every factor there has to be a corresponding another factor such that multiplying those two.
So like not necessarily K, but like there is some
Yeah, yeah,
factor.
yeah.
But okay.
And so
So
I
okay,
basically
so let me just explain what Saptasa is saying. Okay, so now if I arrange these factors in ascending order, that will make my life easier, right? If I arrange them like this, now you can say, hello,
yeah,
Saptas.
yeah, yeah.
Say.
So first thing I take that n is not a perfect square. In that
Oh,
case,
this is n, not 72. अरे बोल दी तो.
uh,
Hmm.
first case I take that n is not a perfect square. In that case, there are even number of divisors, that is factors. So I can pair them up. And in case n is a perfect square, in that case also similarly we can do only the root one. That is, suppose n is k square. So in that case, root over n is k. That
Huh.
the divisor which is k, that can be dealt easy. Like we can just multiply numerator and denominator of that by k. So we get k by k squared. And similarly we can just do it.
Huh.
So only the numerators just add up to 72 and the denominator remains n.
Oh,
Yeah.
okay. Hmm. So basically, like, let us again go back to the prime factorization of. Okay, tell me some other number. 36 ले लो. Someone factorize 2 to the power uh,
That 2 square
square,
into 3 square.
2 square. So what are the factors of 36? 1, 2, 3, 4, 6,
12.
9, 12, 36.
18
Sir, 18
also.
also. Sir, 18 also.
18 also. Good. Thanks. Okay. So now see something, that 1 into 36 is 36. Okay. 2 into 18 is 36. Similarly, we will get relations like d1 dk, d2 dk minus 1. Similarly, we will get, okay. So if I write like this, d1 equal to n by dk. Okay. Then what is 1 by dk? This is simply d1 by n, right?
Yes, sir.
So now if you add them, you will get 72 by n. The problem is if it is a perfect square, then there will be a repetition, and that case is again a homework. Okay, I will not tell you everything. You have to think of it yourself also. Also, I did not write the answer properly because that is again a homework. You have to complete this solution yourself, like full rigorously. I just gave you the how to approach it. Okay, so now let us move forward to the next topic, which is factorization.
Sir, could you please tell me what was the homework you told?
Homework is I gave you the hint now how to approach this question.
Yes, sir.
You write the complete proof yourself. And also I explained it for non-perfect squares. I think about what happens in perfect squares to the middle term. Like here, if this is D1, D2, D3, D4, D5, this is D7, D8, D9. Okay, so
Yes, sir.
D1, D9 equal to 36, D2, D8 equal to 36. All this you will get, but D5 square equal to 36. So here there is a repetition. There is no other D. It is only appearing two times. The 6 square is 36, na?
So, sir,
So
can I
what?
tell what will happen?
Not now, not now. Just complete the proof, bus.
Okay, sir.
Everything if we do in class, then class will not end. Okay, so next topic is factorization. So as you saw, if we factorize the numbers, then many problems become solvable. Like all numbers have prime factorization. That is the fundamental theorem of arithmetic. So now, often in questions like you won't be asked the factorize 72. That is for class 5 students. Okay, you will often be given a very algebraic sort of thing, and you have to factorize it algebraically and then use trial and error or casework or something like that. I will do a few examples, you will understand better. First, let us revise some identities. You all know a square minus b square,
A
a
plus B.
cube minus b cube, all this you know. A cube plus b cube plus c cube minus 3abc. This one also you people know. So let me tell you three identities which are not taught till class 10 and which will be very helpful for us. X to the power n minus y to the power n. Okay. This factorization is given by x minus y into x to the power n minus 1 plus x to the power n minus 2y, so on till x y to the power n minus 2 plus y to the power n. This is the factorization of x to the power n minus y to the power n. So like x square minus y square, x cube minus y cube. These are just special cases of this formula. Using this formula, I can also factorize x to the power 100 minus y to the power 100. Remember the binomial theorem, na? Like you all know a plus b whole square, a plus b whole cube. But using binomial theorem, you don't need to mug up separate formulas. You have one master formula, just put the value of n, you will get x plus y to the power n full expansion. Just like that, this identity is also a very general. You don't need to know what is x square, a square minus b square, a cube minus b cube. You can just remember this, and everyone is a special case of this. Okay. Another formula is x to the power n plus y to the power n. Okay, by the way, this holds for all natural numbers n. Acha, this identity is x plus y into x to the power n minus 1 minus x to the power n minus 2y. Acha, here the signs are alternating. See, here it was a minus, here it is a plus. Okay, plus x to the power n minus 3y square and so on. It will go on till plus y to the power n minus. This is the factorization, but this is only for uh, odd natural numbers. Okay, like you have seen the factorization for a cube plus b cube, na? It is what? Someone tell me.
Sir, a plus b into a
A
square
plus
minus
c
ab
into
plus
a.
b square.
Ah, okay. But can you factorize a square plus b square? You can,
No, sir.
but you need complex numbers.
No, sir.
You cannot in you cannot in real numbers, like you can if you
A plus
include
iota
complex
b into
numbers.
a minus iota b.
Yes, sir.
Very good. Acha, those who are not understanding this part, it is not a part of what I am teaching, it is just extra, so chill. Okay. So this is only uh wait, not factorizable in real numbers. We need complex number. So
Yes.
similarly, this formula is only for odd natural numbers. You cannot factor x to the power 100 plus y to the power 100. You need n to be odd. Okay. Another homework at this point: prove these identities. These two identities using. Can anyone guess what will I
Sir,
say?
binomial
Giving.
theorem.
Okay. I don't know how you will, but
So a plus b also.
induction only you can use the simplest.
Okay.
Prove these two identities using induction. This is your homework. You can also prove them if you know this thing, geometric progressions. If you don't know, then no need to worry. You still have induction, and as I said, that is the power of induction. Even if you don't know geometric progression, you can still prove these identities. That is the power of induction. But if you know geometric progression, then prove them using both methods, both induction and GP. Okay. Now the last identity which I will teach now, a to the power 4 plus 4 b to the power 4. This identity is called the Sophie Germain identity because this factorization was done by this mathematician called Sophie Germain. But I will not write down the answer because you people say how to factorize. And don't Google, okay? Factorize yourself. If you Google, then keep quiet. You have to factorize this. How will you factorize? Any idea?
Sir,
Say.
sir, can we do it like that? If a to the power 4 plus 4b to the power 4 is given, so sir, we can add and subtract 4a square b square.
Okay. Now.
So sir, now we will get a square plus 2b square whole square minus 2ab whole square.
Now,
So sir, it will become a square minus 2ab plus 2b square into a square plus 2ab plus 2b square.
very good. This is the factorization.
Sir, this is only the answer.
Yeah, this is only the answer. A square minus 2ab plus 2b square into a square plus 2ab plus 2b square. This is the factorization. Everyone understood how we factorize this?
Yes, sir.
Anyone who did not follow, I will repeat it. Anyone who did not follow? Okay, everyone understood now. Basically, these two terms add up to 0. So we can add and subtract them, makes no difference. Now, this term, and this term, they form this whole square. And this 4 minus 4 square b square is just 2ab whole square. Now you apply a square minus, not ab, I will say. X square minus y square identity, and you get this into this. Done. Okay, very good. Now let us do an RMO question. Prove that n to the power 4 plus 4 to the power n is always composite. You know composite, everyone knows composite. Composite
Yes,
means
sir.
not
Opposite of
prime
prime.
and not one. So anyone who would like to try? Hint is Sophie German. This came in RMO 1991. Okay, what are your first observations? Someone please tell me. You don't have to solve it completely. Just what comes to your mind after looking at the question? Tell me.
Sir, can we make 4 as 2 square?
We can. Like, why are you asking me? Obviously, you can. If that will help or not, that you can ask. Will it help? But obviously, you can. 4 is 2 square.
Okay, sir.
No, like any other observation.
So we can use a
Huh?
square plus b square.
Huh?
Identity.
A square plus b square, so you can't factorize.
If
How will you use it?
if n is even, then the result is immediate. But if
Yeah,
odd,
very good, very good. So observation 1, for even n, it is trivial. Okay. So for even n, how is it trivial? See, n to the power 4. If n is even, n to the power 4 is what? Even? 4
Yes,
to
sir.
the power n is also even. 4 to the power is n is always
Yes, sir.
even. Even if n is odd, 4 to the power n is even. Wow. So the sum is even. When n is even, see, when n is even, n to the power 4 plus 4 to the power n is also even. Okay. And 4 to the power n is greater than equal to 4 because it is given n is greater than equal to 1 and the only even prime is 2. So this expression has no chance of becoming 2. So if it is even and if it is never 2, so obviously it is divisible by 2 and composite, right? Like just proving a number even doesn't mean it is composite. 2 is also even, 2 is not composite, 2 is prime. But we have also shown that this number is always greater than 2, so it cannot be 2, so it must be composite. Everyone understood this part?
Yes, sir.
Hello. Okay, okay. Now, wait. For the odd, see, n to the power 4 plus 4 to the power n. Na? So I can write this as n to the power 4 plus 4 into 4 to the power n minus 1. So 4 to the power n minus 1 equal to, as someone said, 2 to the power 2 into n minus 1. Right?
Yes, sir.
I want this to be something like a to the power 4 plus 4 b to the power 4. Okay, so I have taken out this 4. 2 to the power n minus 1 is what? See, n is now n is odd, na? Because for n even I have already proven it is composite. Now what we are left to prove that for n odd also it is composite, right? So now if n is odd, then n minus 1 is even, right?
Yes, sir.
Everyone else also please confirm your understanding. See, n is odd implies n is of the form 2k minus 1. So n minus 1 is of the form 2 into, wait, no step there. 2k minus 1 minus 1, which is 2k minus 2, which is 2 common k minus 1. So n minus, n is odd, so n minus 1 is even. Okay. Now, what is 2 into n minus 1? 2 into n minus 1 is 2 into 2 into k minus 1, which is 4k minus 1, right?
Yes, sir.
Okay. So what was our expression? Uh, n to the power 4 plus 4 into 4 to the power n minus 1. I can write this as n to the power 4 plus 4 into 2 to the power 2n minus 2 equal to n to the power 4 plus 4 into 2 to the power 2n minus 2 is what? 2 to the power 4 into k minus 1. So because 2n minus 2 is 4 into k minus 1, we just now showed. Okay,
Yes, sir.
for some k. Huh. So this is equal to n to the power 4 plus 4 into 2 to the power k minus 1 whole to the power 4. Now does this look like a to the power 4 plus 4b to the power 4?
Yes, sir. It is.
So we can factorize it. Now let us factorize. Someone please tell me the factorization. A square means n square plus, uh, wait, what was the factorization? 2ab na? Minus 2ab plus 2ab.
Sir, 2 to the power k.
2 to the power k into n, right?
Yes, sir.
Plus 2 into 2 to the power 2k minus 2. So 2 to the power 2k minus 1. N square minus 2kn plus 2 to the power 2k minus 1.
Sir, it should be 2k minus 2, na?
2b square, na? It is
Yes, sir. So, sir,
2
it should be 2k minus 2.
plus 1 in the exponent. Means 2b square equal to 2 into 2 to the power
Oh, okay, sir.
2k
Okay, sir. Yes, sir.
minus 1.
Yes, sir.
Anyways,
Yes,
let
sir.
me write for everyone. 2 to the power 2k minus 2. This is 2 to the power 1. So this is 2 to the power 2k minus 1. Acha, by the way, everyone is following this. Only one person is saying yes, sir, yes, sir. Hello, everyone, please confirm. Anyone, any doubt, question?
No,
Yeah,
that's
can you
fine.
repeat the last part? The one
Which
you
part?
erased just.
Wait. What did I write? Basically, I factorized this thing. You understood how this becomes this, na?
Yes.
Bus,
Okay.
that's it. Nothing else. We use Sophie German identity to factorize this expression into this expression. Okay. Now, obviously, this thing is minus, so this one is smaller. And the smaller factor has to be greater than 1 if we don't want it to be a prime. So n square minus 2 to the k into n plus 2 to the power 2k minus 1. Okay. This proves that this is greater than 1. Homework. If you can show this, then the proof is complete because we have found two factors, both of which are greater than 1. So this number cannot be a prime, it must be composite. But how to complete the proof? We have to prove that the smaller factor is always greater than 1. Okay, homework. Okay, so now let us move on. Huh. So this also you all have studied. I will just state two things. Number one, uh, you all write GCD or HCF, or what is your notation? How have you learned? Tell me.
The GCD.
Okay, GCD. I have put in my handout, I have just written a comma b for HCF and a comma b for LCM. I have written nothing. But here I will write GCD only. So GCD a comma b equal to ax plus by. We can always find अरे क्या x such that uh, so this is the statement. What does it say? We can always find integers x comma y such that the GCD is a linear combination of the two numbers. Like if you want to calculate GCD of a comma b, then you can write them as ax plus by. You will always find x and y like that. This is called Bezout's theorem. Okay. Now, what is your homework? Obviously,
Can
you
you
can
just
guess
show the last slide? Just scroll up.
more.
Okay. Okay.
Okay. Huh.
I got it.
Acha, by the way, Saptaswa, I wanted to ask you one thing.
Yeah.
So I don't. What should I do? Like, even in HCF LCM, there are many properties and many examples, and after that there is modular arithmetic, etc. So, like everything is written in the handout, and you have already taught it also. So, should I move forward to modular or should I go slowly because we have more classes also?
Yeah, since we have more classes, I think you can go a bit slowly.
Okay, then let me not rush. Okay, so coming back to this later. So maybe the magic trick I will show in the beginning of the next class. I think it will not be possible today, even if it is. Let's see this. So HCF and LCM everyone knows now. HCF or GCD array and LCM. Okay. So let us now visualize it. Suppose A is a number P1 to the power E1, P2 to the power E2, so on till Pn to the power En. Okay. Similarly, B is another number P1 to the power F1, P2 to the power F2, so on till Pn to the power Fn. Okay. Now someone tell me what strikes you first of all.
So they are represented as the powers of the same prime numbers.
Yeah, very good. But is it necessary that they will have the same primes as factors?
Sir, could you repeat?
Is it necessary that they will have the same prime numbers as their factors? Like in both, there is P1 to Pn only, no extra prime in any number. Is it
No, sir,
always
there
like
can
that?
be extra
Hmm.
primes. That means extra numbers there can be.
Yeah, so let us take one example. Give me example. 6 equal to 2 to the power 1 equal to into 3 to the power 1. Okay. And what number is 2 square into 3 into 5? Calculate. 60. Okay. So clearly you can see that here one prime is more. So how is this happening? Tell me. Why did
Sir,
I
can I
take
tell?
why did I take same primes in both? Tell me.
Sir, what I
Well,
have to do, sir? Again, could you repeat?
yeah, like in 60 I have just two primes, 2 and 3. But in 6. But in 60 I have three primes, 2, 3 and 5. Right?
Yes, sir.
I have this extra 5 which I don't have in the prime factorization of 6. But yeah, here we are assuming that P1 to Pn both have the same primes as factors. How is my assumption valid or invalid?
Sir, it is valid, sir, because sir, 6 can be also represented as 2 to the power 1 into 3 to the power 1 into 5 to the power 0.
Yes, very good. So if I write like this, then see we have the same primes in both the prime factorizations. So my point is that this assumption is valid. So let us assume that A is like this, B is like this. Let me just erase this part. Acha, everyone understood na? This 6 and 60 example.
Can you repeat the Bezos theorem part? I missed it. I got disconnected.
Ha, Bezos theorem, I will come back again. So
Sir,
let
it means
us
that
go slowly.
every number is can be represented in the product of every prime number.
Ha, yes. Very good. Like basically n equal to p1 to the power e1, p2 to the power e2. This expansion does not need to end. You can go on forever, but like the primes you don't have, you just
So,
put
sir, why the
power 0.
okay, sir, I got it.
Okay. You just put power 0 in the primes you don't have.
Yes, yes, yes.
Huh. So now my question is also Bézard's theorem. I will come back. Don't worry. Wait. So now my question is, what is the? Acha, you people know GCD. What is the GCD in terms of these primes and exponents? Someone tell me.
What is
Okay,
the GCD of?
A and B in terms of these primes and their powers. Acha, one thing I would like to say that when I was in class 5, all these things were taught to us. And I don't know whether in 5 or 4 or 6, but I am pretty sure you people also know all these. But numerically, you have not learned it in terms of symbols like P1 to the power E1 and all that. But like when you first learned how to take HCF, how to take LCM, what you did was basically what I am saying now, just in symbol in a fancy notation. But it is a very basic thing, and all of you know this. So please tell me, what is the HCF of A and B?
Can I try?
Sir.
We means if each one of the factors p1, p2, p means if we see the powers, if we subtract the greater power from the smaller power and we give it assign it to each prime, that number which will come is the greatest common factor.
So you are saying P1 to the power mod
Greater
E1
one.
minus F1, P2 to the power mod E2 minus F2, and so on.
Yeah.
No, it's not right. Let us take an example only. So, tell me numbers.
I didn't mean that. I meant that the
What you
minimum
meant?
value of which one has. If
Yeah,
the first
correct,
number,
correct. You are
I
correct.
couldn't frame the sentence actually.
Okay, no problem. And you are correct also. So what Spandan means is minimum of E1, minimum of P2, F2. Everyone understood this, right? Let us
Sir,
take
what
an
is this
example.
minimum?
Minimum is minimum. Like minimum of 1 and 2 is 1. Bas, that's it.
Oh, okay,
Simple.
sir. Okay, sir. Oh, yes, sir. Yes.
Okay, so uh, let us do one example. Calculate the HCF of 9 and 12. 9 is how much? 3 square. And 12 is how much? 2 square into 3. Right? What is the HCF? Can you hear me?
Yes, sir.
So 9 is 3 square. 9 I can write 2 to the power 0 into 3 to the power 2. This I can write 2 to the power 2 into 3 to the power 1.
Sir,
Now tell
HCF
me,
will be 3.
2 to the power
HCF
0
will
into
be
3 to the
3.
power 1. That
So
is
HCF will be 3. All of you know using the method you learned in school. But that method is basically this method only. Do you realize how?
Yes,
How do
sir.
you calculate HCF? You just pick the smallest power of each prime and multiply them. Bas. So from 2 to the power 0 and HCF of 9 comma 12 equal to 2 to the power minimum of 0 comma 2 into 3 to the power minimum of 1 comma 2. This is equal to the power 0 into 3 to the power 1 equal to 3. So HCF is 3. Similarly, I am erasing this. Now someone else tell me what is the LCM of A and B in terms of symbols. This is easy. You know the HCF now. You can easily tell me LCM.
Just the maximum, the opposite.
And
Yeah,
maximum E1 comma F1 like that.
yeah, very good. Max E1 comma F1 into P2 to the power maximum of P2 comma F2 and so on. Everyone understood? Let us do the same example again. 9 equal to 2 to the power 0 into 3 square. 12 equal to 2 to the power 2 into 3 to the power 1. LCM of 9 and 12 is how much? 2 to the power 2
2 plus
into
6.
3
36.
square. 4 nines are 36. Yes, very good. Okay. And this property also you all know na. HCF AB into LCM AB is how much?
Product of AB.
AB first. So this also homework, prove it, prove this.
Sir,
Sir.
that the homework
Okay,
which you
so
give now, which
uh,
is the powers will get added. So sir, it would not distinguish between the minimum and maximum. So sir, it would become P1 into E1 plus P1 to the power E1 plus F1 dot P2 to the power E1 plus F2. For HCF and LCM also, and sir, A into B also. So sir, LHS is equal to RHS.
yeah, very good. Basically, what he said is minimum AB plus maximum AB इक्वल टू A प्लस B इसके बाद घर पे करो. I won't complete the proof. बहुत ज्यादा spoil कर दिया already. अच्छा, by the way, do all the homeworks. Prove everything. Proving will make you expert. Without proving, see, Olympiad maths is not school maths. Maths is not about formulae. Maths is like, it is not that I want to calculate this. How will I calculate? I know the formula bus. You have to make your own lemmas, your own theorems. You have to prove things. You have to guess. You have to prove your guess sometimes, disprove your guess sometimes. All this you have to do. You have to think a lot. So prove all these. These are the homeworks. Prove the homeworks. Don't skip the proofs. Skipping the proofs is very bad for you. Very, very bad. Extremely bad. Dangerous. Okay, so now my claim is if there exist x comma y integers such that अरे ये कौन सा है ax plus by equal to 1, then and we are relatively prime. Okay, this is my statement. You know what to do by now.
Sir, prove it.
Very good. Homework proof. Okay. Now, once you have proved this, using this, prove Bezout's theorem. Okay. Don't directly prove it because it may be hard. I'm just giving you a hint basically. Like if you prove this first and then use this thing, then the proof for Bezout's theorem becomes a bit more simpler. So what is Bezout's theorem? Let me restate Bezout's theorem. Hmm. We can always find integers x, y such that GCD-AB equal to AX plus BY. Okay. Okay, now what can you say about X and Y? Someone tell me. Like, what is the highest common factor of A and B? Can it be greater than A or B?
No, sir. Sir,
Everyone,
it can be equal to A or B.
it can be at most equal to the minimum of A and B. It
Yes, sir.
cannot be greater than any of the numbers. Now, if x comma y both are positive integers, then ax plus by will be clearly greater than a and greater than b, right?
Yes, sir.
Even if they are one of them is zero, then also there will be equality only. Okay, so like x comma y both greater than zero, this case is never possible. This is what I was talking about. This is the observation. So in the cases like 3 comma 6, HCF of 3 comma 6 equal to 3 into 1 plus 6 into 0. Here x equal to 1, y equal to 0. Okay. For other numbers, one of them has to be negative, but both cannot be positive, because if both are positive, then HCF will become greater than number itself, which is not possible. Okay. Acha, everyone is listening now. I am not understanding what you people are doing.
Yes, sir. We are listening, sir.
Only you are listening. No one else is listening.
Wherever we are listening, Sukrit is saying everything, so no one is getting a chance.
Acha. Also, if A greater than B, then GCD A comma B equal to GCD B comma A minus B. This thing also proof. Okay. This also you have to prove. All this you have to prove, and please prove everything before Wednesday's class. Complete all the proofs. I will send the handout. You don't need to solve the problems in the handout before Wednesday's class, but you must prove all the theorems, all the properties which I have written down before the class. After that, you can take months to solve the problem. That is up to you. Okay. Now, till now, we have studied only divisibility, factors, etc. Now we will turn to remainders. Okay. Till now, whatever we did, all numbers were perfectly dividing other numbers. But now, while division, there is a remainder which is left. This is the more general case, and everybody knows this from class 3 or 4, I think. A equal to BQ plus R. This is the dividend. This is the divisor. This is the quotient. This is the remainder. Hmm. Okay. So if A equal to BQ plus R, then GCD AB equal to GCD B comma A minus B equal to GCD B comma A minus 2B similarly, and so on. A min A minus QB. Okay. Basically, I applied this formula. This formula I applied Q times. I applied once, I applied twice, I applied few times. So I can write this as GCD of B comma R. Okay. So GCD of AB turns out to be GCD of B and R. R is the remainder. Now can you understand why the Euclid's division algorithm for calculating HCF works? You use the remainder and the divisor to calculate the HCF of dividend and divisor, because dividend is big and remainder is small and calculation is easy for small numbers. So you converted into this. This was taught in class only, na? Hello.
Yes,
I
sir.
couldn't understand.
Sir, could you
Ha.
repeat?
Ade, I said that you know Euclid's division algorithm for calculating HCF. It was done in
Yes,
the
sir.
class only. Huh. So how why is that true? Why is that true? It is true because GCD of AB is GCD of B comma A minus B.
Yes, sir.
Now if I apply again, it will be B comma A minus 2B, B comma A minus 3B till Q times if I apply B comma A minus QB. Now A equal to BQ plus R. So B comma A minus QB is just R. So
Yes, sir. Yes,
GCD
sir.
A comma B is GCD of B comma R. This is the Euclid's division algorithm to calculate HCF, which you did using long division, then took the remainder, etc. Why that works? I gave the justification for that, basically. Okay, calculation and all I won't do because you know. If you don't know, please rewatch the previous lectures. Why don't you know? Huh? Okay, so since we are talking about remainders, it is a nice time to start this new thing called modular arithmetic. Okay, okay, I think I should show the magic now. After that, if we have time, I will tell you the definition of
Bhaiya, you are muted. Still muted.
Acha, hello.
Yeah, now.
Okay. So basically here I have 4 cards, Ace, 2, 3, 4. And here I again have 4 cards, Ace, 2, 3, 4. Okay. Now what I do is, I keep them like this. First of all, let me do it like this. Uh, okay. So basically the magic is, since we are the maths club, we like this word called mathematics. So mathematics, MATHEMATICS. How many letters? 11 letters. Okay, very good. Now what you do? First of all, I am using the selfie camera, so I think my left right is reversed. So this is my right, but it is showing left for you. Okay, so I call this my left, this my right. Now I will pick someone from the audience. Okay, Sabyasachi raises hand. Sabyasachi. Acha, Sabyasachi lowers hand. Anjishnu. Acha, Anjishnu also lowers hand. Sukri.
I think they're not intentionally lowering the hand. It is becoming automatically after some time.
Acha, okay, okay. Acha, who wants to volunteer for round 1? Just unmute and say.
Spandan Mishra.
Sir, I.
Oh, acha, Spandan said first, Spandan. Okay, so what you have to do for, like, I will be, for each letter, I will be shuffling like this, like M, A, and so on. Okay, and we will complete the word mathematics once, exactly once. And like we will complete the word mathematics exactly once, but you can distribute between the two. Like, it is your choice. If you want to do MAT here, then HE here, then MATIC here, and S here. Or you can choose any, like, not even 4, like every letter you can shuffle in other, or you can choose any combination you want. Just tell me what is, like, tell me from the left deck. Tell me the
Okay.
letters.
Start with M and A on the left deck.
This is my left because this is my right. M, A. Okay, twice
Then
I have done.
next two on the
Now
right deck.
next two. Tell me the letters or else I will lose track. M, A done. T, H.
E, H.
Okay. Now
E in the right deck. Left
E
deck.
in the E,
M, A in the left deck or right deck, whichever.
M, A.
Then the rest
Now
three T, I, C, S in the last deck.
T, I,
I, C,
C,
S.
S. Okay, very good. Now I take the top 2 cards. Okay, now I take the top 2 cards and I keep them aside. I keep them here only so that you can see I am not doing anything. Okay. Now for round 2, someone else volunteer. Same thing we will do.
Sir, can I do?
Say.
Sir, MAT on left.
M, wait, I got messed up. M A T on the left.
Yes, sir. Then, sir,
Now
H E on right.
H E on right.
Sir, then M A T again on left.
M A T.
And sir, I C S on right.
I C S on right. Again, I take the top two cards and I keep them aside. Uh, okay, now here I am keeping them. Okay. Also, by the way, the trick is completely mathematical, so I am not deceiving you or anything. No sleight of hands or anything involved. Okay, so for the last round, someone else volunteer.
Yeah, I mean, yes.
Come. Say.
MATH on the left one.
M-A-T-H on the left.
EM
E-M
ATI on this one.
A-T-I
And CS on the right one. Yeah.
C-S. Okay. So I am again taking the top two cards. Yeah, perfect. Ekdom ठीक-ठाक है. Okay. So now I have four sets of two cards each, which were the topmost cards after the 4 rounds, right? And I have not tampered with these cards. You have seen that. Now let me expose these cards. See, both are 2. Okay. Now see this one. Both are 3. Now see this one. Both are S. And the last one, obviously, both are 4. Okay. This was the magic trick. Now what if I tell you this magic trick has everything to do with number theory? कैसा लगा बच्चों?
Yeah, it was nice.
बाप रे बाप,
Sir,
बेशी
quite
हो गया.
interesting.
Okay, so this trick, why it works? It is because of theorem known as Chinese remainder theorem. Okay, and like Chinese remainder theorem allows us to solve for how many cards and how many rounds and what should be the length of the word, etc. So, and I have I have the link of the video in the handout. You can watch after class why it works. But for the explanation, you need to know modular arithmetic. So first, let us start with modular arithmetic. Then we will think about the magic. Okay. So let us start with modular arithmetic. Wait. So this is the notation. This is read as A is congruent to B modulo M. Okay. What this means is A minus B is divisible by M. M divides A minus B. Okay. So this notation is another fancy notation for just this thing. So why another fancy notation? Already we have divides. Why again bother with all this? Basically, like this is true for all of mathematics. You can reduce everything ultimately to basics, but that will just like be a lot of things. And just to shorten stuff, sometimes we introduce new notation standards and all that. And here we are more interested about the remainder than the division. Okay, so like from here, if m divides a minus b, so I can write a minus b equal to q times sum m. So m a equal to qm plus b. So does this look like the Euclid's algorithm? Euclid's lemma?
Yes, sir.
But in Euclid's lemma, I forgot to mention one thing. Here, what is Q? Q is the highest number which divides A without going into negative. Like, wait, let me give you an example. Uh, 5 equal to, not 5, 7 equal to 3 into 2 plus 1, right? I can also write this as 2 into 2 plus 3, or I can write this as 4 into 2 plus minus 1. All these are equally true, right?
Yes, sir.
But what Euclid is saying there is a unique representation where my remainder term R will be from 0 to B. Okay. And the Q is the highest possible without making remainder out of this range. For example, here I can say Q is 2 and B is 3, R is 3. But then 0, 3, 2. This is not true. So this is mathematically true, but Euclid's long division formula is not this. Euclid's long division formula is only for remainders between this range. Okay. But using the modular arithmetic, this modulo sign, I can include all of these cases. Okay. So I can write 7 is congruent to minus 1 mod 2, or I can write 7 is congruent to 3 mod 2, or I can write 7 is congruent to uh, wait, what? 1 mod 2. All of these are true. Okay. For Euclid's division, only we take the remainder in this range, but while modular arithmetic, we can choose anything we want. You understood this now? 7 plus 1 is divisible by 2. 7 minus 3 is divisible by 2. 7 minus 1 is divisible by 2. Okay.
Yes, sir.
Everyone please say okay. Everyone.
Yes, fine.
Okay. Everyone মানে দুজন জেনে নিলাম ঠিক আছে। Okay, anyways, so just keep this definition in mind. Let me just rewrite it. A is congruent to B mod M means that M divides A minus B. Okay. B can be thought of as the remainder. Like B is not always the remainder. Like for example, here 7 is congruent to 1 mod 2. Here 1 is the remainder. But 7 is congruent to 3 mod 2. Here 3 is not the remainder. It is like the remainder only. It is like the remainder only, but according to the this definition and this condition, it is not the actual remainder. Actual remainder is only one remainder is there, and that is 1. All the others are like remainders, but they are not exactly remainders. So again, let us list a few properties. Okay, proof. Anyone say? Not Sukrit. Means I am not scolding you. You are like everything you are only saying is a good thing, but others also need to learn. So don't mind. I am not.
Yes, sir, I understand.
Okay. Okay. So anyone else willing to prove these? Proof, please.
Can I try?
Who?
Spandan.
Right.
If A is congruent to B mod M and B C is congruent to D mod M, then there are integers K1 and K2 such that A minus B is equal to K1N and C minus D is equal to K2N. K2M, sorry. Now we can say that A plus C minus B plus D is equal to 1 second. Yeah, K1 plus K2M. From here we can see that A plus C is equal to B plus D mod M.
Yeah. Very good.
I can't do the second one. I'm trying.
Okay. Okay. Acha,
Sir,
if no
can
one
I
can,
try the second one?
yeah, try.
Sir, if we consider like A, A is equal to MK1 plus B, and sir, B is equal
A
and
equal
C,
to wait. MK1 plus B and
and sir, C is equal to MK2 plus D. So sir, AC will be MK1 plus B into MK2.
multiplication. M square K1 K2 plus MK1 B plus MK2 B plus BD. Right.
Yes, sir. So
So
sir,
AC minus BD equal to M into integer.
yes, sir. Here we can take M common and sir, BD will only will be left. So sir, AC minus BD is equal to 0 mod M. So sir, AC is equivalent to BD mod M.
Yeah, very good. Okay. So we have proved these two properties. Very good. Okay, now I'm stating two more properties which we won't prove. Actually, the proof is like very easy. uh, a to the power k is congruent to b to the power k mod m. Okay. F A is congruent to FB mod m, where Fx is a polynomial with integer coefficients. Again, homework, prove them yourself. Okay, homework, prove them yourself. Another property is
Sir, could you please scroll up a bit?
more.
No, sir, here only, sir.
Okay. Done.
Yes, sir.
Basically, what this property is saying. Wait, first let me highlight this. Hmm. So what this property is saying is that, like we had this multiplication rule, na, that A congruent to B mod M, C congruent to A congruent to B mod M, C congruent to D mod M, you can just multiply them. AC is congruent to BD mod M. Okay. But you cannot divide them always. Like CA congruent to CB mod M implies A congruent to B mod M. This is not always true, huh? This is not always true. Let me just make that sink in your mind, please. Don't divide, don't divide, don't divide. It is not always true. It is only true in this very special case. It is only true in this very special case. Okay. Now, why is it true in this case and why is it not true in other cases? Proofs and examples, homework. Okay. So, what is your homework? This property.
Sir, do we have to send them to you?
No, you have to just solve them. Be
Sir, can we send?
obedient and sincere, and if you send, I won't check.
Okay, sir.
If everyone starts sending, how will I check someone?
Okay, sir.
Anyways, so another homework, all the properties we have studied till now, find examples, numbered examples. Okay. For example, when is this property true? Try it using some numbers. When is this property not true? For like the GCD is greater than 1, it is not true. Why is it not true? Find an example where it is not true. Find examples of all the properties we have learned till now. Okay, that is another homework. Okay. Now, what is special about this modular arithmetic or remainders in general, that it is like a cycle. like a number line is like this now, 1, 2, 3, 4, so on till infinity. But in modular arithmetic, it forms a cycle. The cycle is exactly like a clock. Okay, I am drawing a clock. Okay, uh, so like if it is 1 o'clock right now, then after 12 hours, it will not be 13 o'clock. It will be 1 o'clock again. So like after 11, it is 12. After 12, it again comes back to 1. So like it repeats. It forms a cycle, modular arithmetic. Like obviously you can go to 13 also, but 13 is also congruent to 1 more 12, right? So 13, 1, everything is same from the point of view of 12. Okay. So this is like a clock. So modular arithmetic is used in such places. Even days of the week, like after Sunday, it is not some eighth day. It is Monday only. Okay. Like if Monday is 1, Tuesday is 2, so on. Saturday is 6, Sunday is 7. Okay. Then the eighth guy is again Monday, which is again the first guy. Okay, so 8 is congruent to 1 mod 7 again. From the point of view of 7, 1 and 8 are the same thing, does not differentiate. Okay, very good. So this hmm. Now here are some properties. Again, prove them yourself. Um,
Sir, can we do one proof here?
no, I don't have so much time actually.
Okay, sir.
Acha, Saptaswa.
Yeah.
Farmers little theorem পরের দিন করবো না আজকে করবো?
হ্যাঁ, ওটা পরের দিনই করে না, আজকে 6টা বেজে গেছে যখন।
ঠিক আছে. Okay, so I'm just listing a few properties, or actually these properties are listed in the handout only. Okay, they are written exercise. Just complete all the exercises. There is nothing more to say in the class. I better explain Farmer's little theorem. It's a very small and cute proof. That will be better. I'll just take 10 minutes more, I think. So again, format is everywhere. So what does Fermat's little theorems say? If A is a positive integer and P is a prime, then A to the power P is congruent to A mod P. This is what Fermat is saying. This is his main claim. This is the theorem. Okay, very good. Now, if GCD of A comma P equal to 1, then what can we do? What have you learned in the previous section? If GCD
Sir,
is 1,
ax
then
plus py is equal to 1.
yes, okay. But in modular arithmetic, like What is that operation we can only do when this HCF is 1?
We can multiply with divide with the same thing.
Yeah, we can divide. So very good. Here see, CA congruent to CB mod M. If C and M have HCF 1, then only A congruent to B mod M. Okay. So here I can cancel by 2. We can cancel by A actually. So if I divide both sides by A to the power P minus 1 is congruent to A mod P. This is only true when this is true. Otherwise it is not true. Okay. Many people think this is Fermat's little theorem, but this is a special case. This is the actual theorem. Okay, this is the actual theorem. A to the power P is congruent to A mod P. This is the actual theorem. This special case is only true when the HCF is 1. Now let us prove this theorem. Acha, how many of you don't know anything about combinatorics?
Sir, I know a little bit.
Acha. Okay, before that, let me just tell you that like a square plus b square equal to c square implies the triangle is right angle, right?
Yes, sir.
If triangle has a, b, c sides. And if the triangle is right angle, then a square plus b square is c square. This statement is true both ways. Okay. If triangle is right angle, then this holds, and if this holds, then also triangle is right angle. So Pythagoras theorem and its converse both are true. But in Fermat's little theorem, the converse is not true. So okay. So like we take it for granted sometimes, we do not think deeply, but often converses of theorems are not true. Fermat's little theorem is one such example. Pythagoras theorem, in Pythagoras theorem, converse is true. For example, 2 to the power 341 is congruent to 2 mod 341. How do I know this? Homework. Okay. You have to prove homework is proof. Prove it. Without calculators, obviously. But that is not what I wanted to show you. What I wanted to show you is 341 equal to 11 into 13. 341 is not a prime. Okay. So for P prime, A to the power P is congruent to A mod P. But A to the power P congruent to A mod P doesn't imply that P is prime. Okay. This part is wrong. It may not always be. Here is the example. 2 to the power 341 is congruent to 2 mod 341. But 341 is not a prime. So keep that in mind. Okay. And can I take 5 minutes more? Or should I do it in the next class?
Sir, can you do it in the next class? Actually, I
I
have
have
another
to. I
class
do
now.
have class.
Okay. Then let us end this. Okay, stop the recording now. If you have any doubts, please tell me. You can stop the recording. Ayush. Hello, Ayush.
Yes, Dada.
Recording stop.
Okay.